All right, today we're going to start a series on soil. Just so you know where I'm getting my information, I'm using my notes from college when I studied to get a plant and soil science degree from Texas Tech. So if there's any Red Raiders out there, that's awesome. If not, you might want to look into Texas Tech. They have a really good plant and soil science program. Um, I'm sure there's some biases in general out there, so I'll just throw that out there. But anyways, what I intend to do is to share some basic definitions of soil, and this can be like sort of a building block for the next things that we're gonna have to go over for doing multiple videos. So soil is the unconsolidated material at the Earth's surfaces that serves as a media for plant growth. And it's dynamic. It's a dynamic three-phase system comprised of solids, liquids, and gases. So that right there might be kind of something that you haven't thought of. You might think of soil as 100% solids, but 50% these are generalities, but just for starting out to get kind of a baseline. 50% of the soil is solid by volume, and 25% of the soil is liquid by volume, and 25% of the soil is gas by volume. So the solid portion of soil is inorganic, non-carbon based or carbon-based materials, but 95% or more of this material will be inorganic. Usually it's closer to 100%, or at least farther away from 95%. Basically what I'm saying is that a very small portion up to 5%, but usually not even up to 5% of the soil is actually organic matter. Okay, so the inorganic soil solids are broken down into three types, and they're called textures, and they are sand, silt, and clay. And sand is 2 millimeters to 0.05 millimeters in effective diameter, which is the sum of the height, width, and length divided by 3. So that same definition of at the end, sum of the height, width, and length divided by 3 is the same for sand, silt, and clay. Their shapes are different, so that's important to know. Silt is 0.05 to 0.002 millimeters in effective diameter, and clay is less than 0.002 millimeters in effective diameter. So sand should be thought of as having a spherical shape. And then if you broke down sand particles into several smaller silt particles, those should also be considered spherical shaped as well. Clay particles, on the other hand, are more of a box sort of shape with one long axis. So if you've ever ordered something in the mail that came in sort of a long cardboard box, let's say that you ordered an umbrella, maybe it would come in that sort of box, right? Where the handle makes it be a wider box, but it's shallow, and then the length is it's pretty long. So that's clay, and they have a very large surface area per unit volume, and that has all kinds of effects on soil chemistry later on, and it has to do with charges, electric charges in the soil, and how the soil is able to hold ions, chemical ions, and that's important when we're talking about holding nutrients. So the shapes actually have a pretty profound effect on soil in general. So other material, you would classify gravel as being, so now we're out of soil. This isn't soil anymore. This is other earthy material. And gravel is going to have 2 to 75 millimeters. 75 millimeters is about roughly 3 inches. Not exactly, I guess, but roughly 3 inches. And so you can see from the very last stopping point of the maximum size of sand, from there, that's where gravel starts. That's the size that gravel starts. So 2 millimeters up to 75 millimeters is gravel. Cobbles are 75 to 250 millimeters. Stones would be classified at 250 to 600 millimeters. And then boulders would be greater than 600 millimeters. Okay, so back to soil being solid, liquid, and gas. The dynamics of the soil system occur in the liquid and gaseous phases. So the solid phase of soil doesn't really have a lot of ability to be really dynamic. If you're saying that makes sense, it can't move around so easily. It's more of a static thing. It's not really static because it can move with temperature and potentially moisture content, but the gaseous and liquid dynamics are the dynamic parts of soil, the soil system. So the liquid phase is water with dissolved inorganics, and I was saying maybe it's not always water. Maybe there's some sort of plant oils or something like that, right? But generally speaking, it's going to be water. So the liquid phase is water with dissolved organics such as fertilizer salts and soluble organics such as natural organic materials and pesticides. Hopefully not. In my opinion, I would rather not have the pesticides in there or the inorganic fertilizers where it can be helped. Some are naturally inorganic. That's a slippery definition and too much to go into right now. But some things are just simply like made out of parent rock, like sulfur is not. It can't be organic. It's an inorganic. Basically, when you buy sulfur, it's elemental sulfur. It's just sulfur. It's like if buying salt and saying, well, it's organic salt. Well, it can't be organic because it literally doesn't generally have life in it. So you gotta, I guess I did kind of go into it a little bit, but you gotta kind of think of it that way. But that was just kind of a bunny trail back to soil and its different phases. So as water is added by rain and irrigation and snow melt, the liquid fraction of the soil increases while the gas phase decreases. So the liquid water, like it was saying, is, like my notes were saying, is displacing the gases. And then once that water is drained out, then the gases will return naturally. I'm not going to get too deep into that. There's a lot of ways that it may not come back as much but that's not for right now. When water is removed from the soil by drainage, evaporation, or transpiration, the liquid fraction of the soil decreases and the gaseous phase of the soil increases, like I was saying. The composition of the soil atmosphere, which is the gaseous phase, is similar to that of the air atmosphere. So, soil atmosphere being the atmosphere in the soil, and the air atmosphere being the atmosphere that we're breathing. It's very similar because the same gases are infiltrating the soil, but because plants are using those gases differently and releasing some gases differently under the or in the soil, it's a little bit different, but it's very similar. So the air atmosphere is about 78% nitrogen gas, N2 gas. The soil atmosphere is 78% N2 gas also. The air atmosphere is 21% oxygen, O2 gas. The soil atmosphere is less than 21% oxygen, O2, but close. The air atmosphere has 0.03% CO2, and the soil atmosphere has more than 0.03% CO2. But it's oftentimes closer to that 0.03. But those are the two numbers that are going to move the most, is the oxygen and the CO2. And then 1% argon. And the nitrogen and argon percentages don't really change because they're not consumed or modified by the plants or most microorganisms. Although there are exceptions that are important, whereas nitrogen gas can be taken up by certain nitrogen-fixing bacteria called rhizobium in beneficially infected roots of certain plants, specifically legumes. Almost all the time they're legumes, but that's still not going to change the composition of the soil atmosphere very much, but it's something to note. And oxygen is consumed by plant roots and microbes as parts of the respiration process below ground. And the soil atmosphere therefore contains less than 21% O2. And then carbon dioxide, as those are kind of two things that are moving in tandem in opposite ways, in opposite directions. Carbon dioxide, meaning that's the second one, oxygen or carbon dioxide, is produced by respiration, and the soil atmosphere has greater than 0.03% CO2 because of that. And so when it's talking about respiration, we're talking about plant roots where most of the carbohydrates that the plants make are stored. Those, when they're used, they are breaking apart those sugars, C6H12O6 molecule, the basic molecule. There can be different molecules, but that's the basic building block, basic carbohydrate. And so when that happens, the plants are using up O2 and releasing CO2. And so therefore, that's why the soil contains less than 21% oxygen or O2 and greater than 0.03% CO2 as opposed to the air atmosphere. Now, if there were no plant life, is if there's no plant life in that soil and no organic matter breaking down, and nothing else happening, say it was just sand on a sand dune, that may not be true. They may be the same or close to it. But just so you understand that these are dynamics, these are dynamic systems, and these are some of the things that put pressure on those one way or another, or maybe pressure is not the right word, but are pushing on that balance one way or another. I'm going to stop the video right there, and the next video I think is going to be the soil forming factors. So instead of having all of that in one video like I was thinking to, because this video is already 15 minutes, 16 minutes, I'm going to go ahead and end the video right there. Please leave feedback, comments. If I missed something, if I got it off or whatever, misremembered something or whatever, feel free to put that in there. Anything that you can add, go for it. And that's it. My name's Jonathan. Have a great rest of your day.